Alright, welcome back, guys. We're going to finish up chapter 4. I'm not sure if we'll do it in one video or not. We'll kind of see how it goes. We may have to break it up into a couple videos. But anyway, we're going to be talking about what are called binomial probability distributions. So this is a specific type of a discrete probability distribution, okay? Because the random variable can only assume discrete values, okay? So like 0, 1, 2, 3, 4, etc. And that's what we talked about last class. We looked at the difference between a discrete versus a continuous random variable. We looked at developing or making a discrete probability distribution. We also looked at finding the mean, the variance, and the standard deviation of those distributions. And we also talked about the expected value. Okay, so today we're going to, if you look here, go over the learning objectives. It says we're going to look at how to determine whether a probability experiment is a binomial experiment. Furthermore, how to find binomial probabilities using the binomial probability formula, and then how to find binomial probabilities using technology, formulas, and a binomial probability table. So I'll show you, I'll reference that table in the book just real briefly, but for the most part, guys, we're going to be using technology. And then how to construct and graph a binomial probability distribution. And then finally, similar to in line with 4.1, we're going to be looking to find the mean, variance, and standard deviation of a binomial probability distribution. Okay. All right. So first of all, what does this term binomial mean? Okay. Well, we know that prefix bi refers to 2. So we call a probability experiment in which there are only 2 outcomes, we call it binomial, okay? And we deem those outcomes to either be a success or a failure. So that's basically it. So an example, well, the most commonly used example would be flipping a coin. When you flip a coin, there's 2 outcomes. There's either heads or tails. And we could assign a success and failure to each of those outcomes. So if we were interested in the coin landing heads up, we could assign heads to be the success and then tails to be a failure. Okay? So it's always going to apply to things in which there are only 2 outcomes. All right, so this is the definition. These are the criteria that it has to meet in order to be a binomial experiment. Okay, it has a fixed number of trials. So think about flipping a coin. Okay, so let's say I'm going to flip a coin 10 times. So that would be a fixed number of trials. And each trial is going to be independent of the other trial. So if you recall what that means when referring to events, the independence of 2 events means the outcome of one event does not affect the outcome of another event, okay? And that's actually what happens when you flip coins. Okay, so that's the first criteria. Then the second is there are only 2 possible outcomes of interest for each trial, and we can deem one a success and we can deem the other a failure, okay? And then thirdly, the probability of the success is going to be the same for each trial. And really that's because these are independent. Okay, well, that's one reason. They're independent, and the probability, because of that, the probability of achieving a success is never going to change, okay, from event to event or from trial to trial. And then lastly, the random variable x is typically we let x count the number of successful trials. So in line with that example of flipping coins, guys, let's say I flip a coin 10 times, I could let x count the number of heads that I get. Okay, so x could assume a value anywhere from 0 to 10 inclusive. Now the probability that x is 0, meaning that I flip a coin 10 times and I get 0 heads, that probability is very low, but it's not 0. And furthermore, the probability that if I flip a coin 10 times and every single time it lands heads, or in other words, the probability that my random variable x assumes a value of 10, that's also going to be pretty low, because, you know, intuitively that's rare. And in fact, well, we'll talk more in line with expected value. The expected value of x in that example would be 5. If you flip a coin 10 times, you would expect about 50% of those flips to have outcomes of heads. Okay. All right. Let's continue. Okay, so we use these variables to represent these different parameters. So n is always going to represent the number of trials. Okay, so it could be the number of flips, it could be the number of draws, it could be the number of surgeries, as you'll see later on. And then p is always going to represent the probability of a success in each of those trials. Okay, and the value of p is never going to change. It's going to be fixed. And then q is going to be the probability of a failure. Okay, so look what's written right here, guys. Q is also equal to 1 minus p. And if you remember, because those are complements of each other, if each trial or if each event can only have 2 outcomes, and the probability of one outcome is p, then the probability of the other would have to be 1 minus p, okay? Because those are mutually exclusive events, right? You can't, you know, flip a coin and have it both come out heads and tails. That's impossible. All right, and then x, that's going to be our random variable, okay? And it represents a count of the number of successes in n number of trials. So what we deem to be a success and what we deem to be a failure, guys, that's just arbitrary. I could just as easily say, okay, I want to let the outcome that the coin lands tails up be a success, okay? All right, so here's an example, a little visual example here. So evidently what we're doing, or what we appear to be doing right here, is we're drawing cards, okay? And these, in order for this to, you know, for each draw to satisfy those conditions, we would have to be replacing the cards, so that each time there's 52 cards in the deck. So the probability of me drawing a specific card or a specific subset of cards is the same for each trial. So here you can see, if for your first trial or draw you draw a 10 of spades, that's a failure. And then a 9 of clubs for your second draw, that would be deemed to be a success. And then an 8 of hearts would be deemed to be a failure. A 5 of diamonds would be a failure. And finally, a jack of clubs would be a success. So we've had a total of 5 trials, and 2 of those trials yielded successes. So the value of x here, our random variable, which counts the number of successes, would be 2. And we could assign a specific probability to that. Okay, and that's what we're going to talk about later on. But anyway, also, sort of a side note, I bet what we're deeming to be a success here, guys, is that the card is a club. Okay, because notice, you know, only these 2 cards were deemed successes, and they both happen to be clubs. So anyway, let's continue. So now what we're going to, so like I said, the most classic example of binomial distribution, or that will give you a binomial distribution, is flipping a coin and counting the number of either heads or tails. Okay. So suppose we flip a coin 4 times and we count the number of heads that we obtain in the 4 flips. So using the definition above, It says explain why this is an example of a binomial experiment and identify the values of n, p, and q and all the possible values that are going to be in the sample space of the random variable. Okay. All right, well, we've talked about this. We know that each trial is going to be independent. Okay. The probability of flipping a heads for each trial or each flip, that's always going to be 0.5 unless the coin is weighted. Let's see, what else? Yeah, I mean, that's pretty much it. The probability for each trial is fixed. There's only 2 outcomes. And then, of course, X is measuring the number of successes. So we'll go ahead and give these parameters values. So if we're flipping a coin 4 times, then the number of trials is going to be 4. And then the probability of a success, or the probability of flipping a heads, is going to be 50%, okay? Which means the probability of a failure would be 1 minus 50%, or 100 minus 50%, which is also 50%, okay? And then X, of course, here would measure the number of flips that were actually heads, okay? So X could have, well, let's just go ahead and do this, because all the possible values that X could have, X could equal either 0, okay, could equal 1. You could have 1 head out of those 4 flips. It could be 2, it could be 3, or it could be 4, okay? So these would all be values in the sample space. These are all the values that X could assume for this particular example, okay? All right, example 2. Guys, I've been under the weather for a little bit, so my voice may sound a little extra monotonous, I guess I should say. Anyway, so let's look at this one. Again, we're going to decide whether each of these experiments is that of a binomial experiment, and then if it is, we're going to identify the success and the values of these parameters n, p, and q, and then again list the possible values that X could assume, or in other words, the sample space, okay, for that random variable. All right, number 1. A doctor performs a surgical procedure on 8 patients. So there's a 90% chance of the patient having a full recovery. All right, so this is more like a real, well, the coin one is a real world example as well, but this one is as well. So you could deem each surgery to be a trial, okay? And so there's only going to be 2 outcomes here. The patient will either have a full recovery or will not have a full recovery, okay? At least that's the way we're looking at this. And furthermore, guys, we can probably assume that the outcome of each of these surgeries is probably independent. Okay, so we can look at these 8 different surgeries to be independent events. So because of those aforementioned things, we can assume that each of these surgeries, this would be a binomial experiment, okay? And consequently, we can give values to these parameters. We can say, since there are 8 surgeries, n is 8, or 8 trials, we're going to let the patient having a full recovery represent our success, okay? You could do it the other way. I guess maybe you're a bit malevolent. But anyway, if we're deeming a full recovery to be a success, then the probability for that is going to be 90%, okay, or 0.9. And then that would leave us with only 10% probability for the patient not fully recovering, okay? And then as far as the sample space goes, X can take on a value anywhere from 0 all the way to 8. And this is how it's always going to be, guys. Right? Because if you have 8 trials, then there's anywhere from 0 up to 8 possible successes in that sequence of 8 trials. So this would be the sample space for the values that our random variable x could assume. Now, I want to say something else. Because the probability that the patient has a full recovery is rather high, 90%, you could expect that the majority of these patients would recover. Or in other words, guys, the expected value of x, which counts the number of recoveries, would be closer to 8. It's going to be further to the right over here, okay, and further to the left. Now, if the chance of recovery was fairly low, then we could expect expected values of our random variable to be fairly low as well, okay? And I think we sort of know this intuitively, right? Okay, number 2. It says, a box contains 4 red tokens, 5 blue tokens, and 2 green tokens. So 3 tokens are selected randomly without replacement, and then the random variable represents the number of green tokens. Well, let's see here. First of all, we need to determine, is this binomial, before we go any further. And guys, it hinges upon this word right here, without replacement. Because see, when you fail to replace a token, you are in a sense reducing the size of the sample space. And the likelihood of that next event is conditional upon the outcome of the previous event. Remember when we talked about conditional probability? So if you assume that we're not replacing these tokens, then these events are not independent. So therefore, this cannot be a binomial experiment. So I'm going to put in here no independence. Okay, and so this implies that it's not binomial. Okay, what about number 3? Number 3, it says a survey found that 68% of adults ages 18 to 25 think that their generation is unique and distinct. So 12 adults within this age group are randomly selected. The random variable represents the number of adults in this age group who think that their generation is unique and distinct. Okay? So you got to look at it this way. We're selecting 12 adults. Okay, so we can think about this as there being 12 trials here. We can furthermore assume, guys, that these are going to be independent. Okay, the outcome, however one respondent answers, that should not affect the likelihood of, or that should not affect the way the next respondent answers. Okay, so we can assume independence here. And furthermore, we can also assume that the probability that each of these respondents thinks that their generation is unique and distinct is going to be unchanged. The likelihood of them answering yes to this survey question is always going to be 68%. Okay? So, the parameters would be 12 number of trials here, because there's 12 adults within this age group being selected. The probability of a success, well, we've deemed a success to basically be that individual saying, yes, I think my generation is unique and distinct. So the probability of that is going to be 68%, or 0.68, which leaves the probability of a respondent saying no is going to be 1 minus 0.68, which would be 0.32, okay? And then as far as the number of outcomes for our random variable x, it could be anywhere from 0 I'm not going to list every one here, guys, all the way up to 12, okay? Could be such that every one of those 12 selected answered yes, okay? All right, so that's a little bit of practice, just identifying whether or not something is a binomial experiment or not. And by the way, guys, I just mentioned there are other types. There are called multinomial experiments, and they're very similar in a way, but they're not just two outcomes. It could be like 3 outcomes or 4 outcomes, but the probability for each of those outcomes is fixed. All right. Okay, so now we want to get into trying to figure out, well, what would the probability be? Let's say, we were to actually do this and survey 12 of these individuals. What is the probability that X has a value of, say, 10? Or in other words, we're asking, what's the probability that 10 of those respondents say yes? Okay, or what's the probability that 9 say yes or 8 say yes? So to each value for X, there will be an associated probability. So we've seen this before in 4.1. Because this is a discrete probability distribution. All right, so let's talk about this before we talk about a formula. So let's go back to flipping the coin, okay? So to determine the total number of outcomes, you guys remember we can use the multiplication rule, right? You say, for my first flip, there's 2 outcomes. For my second flip, there's 2 outcomes. For my third flip, etc. So there's 2 to the 4th outcome. So there's 16 different outcomes for our experiment. But remember, we're not, what are we counting? We're counting the number of heads. So what we have here listed are all the outcomes, okay? Every single flip could be a head, or every single flip could be a tail. But if we're interested, so here in this particular example, well, let me just read this. It says, when we consider the random variable X, the number of heads in 4 flips, the order in which the heads and tails occur doesn't matter, right? Because we're just counting whether there were 2 heads or 3 heads or 4 heads or 1 head, right? The order in which they occur in the 4 flips makes no difference, okay? So let's just arbitrarily say we're interested in finding the probability that X is equal to 3. The probability that our random variable X assumes a value of 3. Well, in the context of this problem, that means what's the probability that if you flip a coin 4 times, you'll get exactly 3 heads? Well, there's 4 outcomes that satisfy that. Outcome number 2, outcome number 3, outcome number 5, and number 16. Each of these outcomes has exactly 3 heads, okay? So we could determine the probability that in 4 flips, our random variable, which counts the number of heads, is equal to 3, is going to be 4 out of 16. So this would be using that theoretical approach to probability, okay? 4 out of 16, or in other words, 1/4, okay, or 0.25. So you could do this anytime you want to try to calculate the probability that X assumes a certain value. You could literally list out all of the potential outcomes and then find all the outcomes that satisfy X being a specific number, okay, or that particular event in which X is that specific number. But that's going to be a lot of work, guys, okay, because what if there were like, 10 flips and not just 4? Well, 2 to the 10th power is a huge number, so that approach is not going to be very practical. So we're actually going to employ a formula that takes everything we've kind of talked about into consideration. That the probability for each success stays fixed. the probability for failure also stays fixed. And then the order in which these successes occur does not matter. Okay? And if you think about that, mathematically what that means is this right here. Okay? This is the formula. This is called the binomial probability formula. Okay? So in a binomial, now don't freak out, first of all. Okay? I know, it may look a bit intimidating, but it's actually not that bad. And we're, for the most part, going to be using technology to evaluate it anyway. So let's talk about this for a second. Okay, so the probability of exactly X successes and N trials, or in the context of that last example, the probability of 3 heads in 4 flips. Okay, so you're letting your value of X be 3. We know what the value of P and Q are going to be, right? These are always given to us in the context of the problem. We're going to know the value of N, that's the number of trials. And we'll know the value of X, okay? Because that will be associated with the probability that we're trying to find. So we'll be using a combination, and this is the formula. So if you think back to section 3.4, N objects chosen X at a time, okay, that would give you this formula right here. We've got some factorials involved. And then you'd multiply this by P to the power of X and N times Q to the power of N minus X. So in the context of that last example, what's the probability that if you flip a coin 4 times, you get exactly 3 heads? Well, my parameters, I'll just go ahead and write them down real quick. N would be 4, P would be 0.5, which means Q would also be 0.5. And then here we're letting X have a value of 3. Okay? So what you would literally do, guys, is just plug these numbers into this formula. And that's what's been done here. Okay? Now this exponent 4 minus 3 just becomes 1. And so 0.5 to the third times 0.5 to the first. If you add exponents, you get 0.5 to the fourth. And then 4 objects chosen 3 at a time, there would be 4 combinations. Now if you were to do this math, you'd get 1/4. So you would get what we found previously. Okay? Now let's interpret this formula a little bit. We sort of already talked about it. The part right here, the P to the X times Q to the N minus X, this follows from the multiplication rule, okay? Because these trials are independent of one another, okay? We're simply multiplying the probability of X successes and the N minus X failures together, okay? N minus X represents the number of failures it will have. X represents the number of successes. So see, it would be the number of successes times the number of failures, and that would be a total of 4, right? And then, let's see. Oh, right, yeah. But this part only gives us the probability of a single outcome. And we've seen previously how the order in which those successes appear doesn't matter, okay? So that's where this combination part comes in. This represents the number of different ways of arranging X of those successes in different trials, okay? So you could have all the first 3 flips be heads, or the last 3 flips be heads, or 1 head followed by a tail, and then 2 more heads, okay? So the combination part takes into account the fact that we don't care about the order in which those successes occur, okay? So all of this together, if I look back up here at the actual formula, this will allow us to calculate the probability that X assumes any given value from 0 to 4 in the context of this example. Okay. All right. And fortunately for you guys, we do have a function in the calculator. Okay, it's called binomial PDF. PDF represents probability distribution function. Okay, and we will use this. I don't know if I use it for the very first one, but we will for some others. Let me go ahead and show you where it is. So of course you could read the notes, but you need to go to this distributions right here function. So you have to hit second and then the variables key. And then you're going to scroll down, and it's this one right here. Now don't confuse this one with this next one because they look the same, except this is a probability distribution function. This is a cumulative, well actually this represents probability density function. We won't really go into that, but this one represents cumulative density. We will use this second one here after a while, but anyway, this is what you would use. Now, if you've got one of the newer calculators, it'll ask you for the number of trials, it'll ask you the probability of a success, and then it'll ask you what value of X are you looking for. Now, you may be wondering, why isn't this asking me a value of Q? Well, the calculator doesn't need that. The values that define the experiment are N, P, and X. That's it. The calculator can find Q. It can just say 1 minus P. Okay. Anyway, that's where it is. Now, if you've got one of the older calculators, it won't prompt you. It'll actually, well, it'll open a set of parentheses, and you'll have to put in those parameters, N, P, and the value of X. Okay, and close those parentheses. Anyway. All right, so let's try one. Let's look at example 3 here. So it says rotator cuff surgery has a 90% chance of success. So the surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 of those patients. All right, well, let's define our parameters here. So if it's 3 surgeries, that means N is going to have a value of 3. And if the probability of a success, this is a coincidence, using that word, of course, is 90%, so 0.90. I'm not even going to put in the value of Q. Well, yeah, I guess I will. It would be 0.1, okay? And then we're trying to find the probability that exactly 2 of those surgeries, are successful, okay? Now, what I want to do on this very first one is I want to show you how to use that formula if you were going to use it. So the probability that X is equal to 2. So this is N, well, let me rewrite the formula up here. Probability of X, that X is equal to a certain value is X, no, I got that backwards. It's N, choose X objects, times P to the power of X, times Q to the power of N minus X, okay? And then for that combination, well, put this over here. It's X, no, I'll get this right eventually, guys. It's, yeah, it's N factorial. N factorial divided by X factorial times N minus X factorial, okay? Yeah. All right, so you're just gonna plug in these numbers if you're gonna do it manually. Okay, so N is 3, so we'd have 3 factorial divided by X is 2, so 2 factorial, and then 3 minus 2 factorial, well that's just 1. And then this would be multiplied by p to the power of x, so p is 0.9 to the power of x, which is 2, times q, well, q is 1 minus p, so 0.1 to the power of 3 minus 2, which is the same as 1. So we could simplify this sum. 3 factorial is 6. 2 factorial is 2. And then right here, 3 minus 2 is 1, and 1 factorial is just 1, so don't worry about that. So all this simplifies to just 6 divided by 2, which is 3. Okay, so just put a 3 right there. And then this would be times 0.9 to the second power times 0.1 to the first power. Okay, and then you could use your calculator and just plug these in. So even if you're doing it all manually, it's not going to be that bad. Okay, so 3 times 0.9, raise that to the second power, and multiply this by 0.1, and we get 0.243, 0.243. Okay, so the probability that x equals 2, or in the context of this problem, that exactly 2 of those 3 surgeries are successful, is 0.243. Now, I want to show you using the probability density function. Okay, you could do this. Okay, so we have 3 trials. Probability of success is 90%. And the value of x is 2. Okay, so just hit enter, and it actually pastes it in that format that I was telling you. Okay, it's just that that interface actually collects the values for those parameters, and then when you hit enter, you can get the same thing. Okay, and of course, you know, Excel will do this as well, guys. In fact, I was using it here to create a graphic that we'll see further on in the notes, but you can hit enter and come over here, go to more functions, and there's a binomial distribution function right here. Okay, and then it'll ask you those parameters. See, so I could put in 3. Oh, wait a minute. You gotta be careful how you read this. Okay, so the number here means the value of x. How many successes? So 2. The number of trials is 3. And the probability of the success is 0.9. Okay, and for this cumulative part, you would have to put false, because we'll talk a bit about this later on. The cumulative part means it will calculate the probability that x took on a value up to and including 2. But all we want to know is what's the probability that x is equal to 2, or in other words, there were exactly 2 successes. So you just type in here false, and then if you hit enter or OK, it'll calculate that probability for you as well. So anyway, all right, let's try example 4 then. Oh, while I'm on it, guys, since I'm showing you different ways to find this using the calculator in Excel, why don't we go ahead and take a look at the table, okay? So I'm just using the table from the book. If I can find it, we've got about 1,000 windows open. So what I did is I just went to the appendix in your digital textbook, and so what you'll see here is, and I used to use these tables when I was in college. Not that we didn't have technology then, it's just I rather enjoyed it. But anyway, you can see here this first column lists the number of trials. So in our case, it was 3 trials. Okay, so you'd be focusing on this big row right here. And then next to that, it gives the number of successes. So whether 0 successes, 1 success, 2 success, or 3 successes. Okay. Well, we were interested in knowing 2 successes. Okay, so you'd be looking just in this line right here. And then to figure out which value it is, you look up here at this horizontal axis and you find the probability of a success. Well, the probability of a success is 0.9. So we would be in this column, and that row that I just talked about, it would be, whoops, highlighting the wrong thing, it would be right here. See that? 2 successes, a value of 2 for x when n is 3, which corresponds to 0.9, the probability of each success. Okay, so these tables are pretty nifty. You know, before the widespread use of digital computing, this is what people used. And these tables had to be computed, so there was a lot of work that would go into creating a table like this. And then sometimes you might need more accuracy, so you might have tables that had even more digits behind them instead of just, you know, to 3 decimal places here. But anyway, all right, let's go to example 4. Okay, so if any of you are soccer fans, it says Argentine soccer player Lionel Messi converts 78% of his penalty kicks. I'm not really a soccer fan, but that seems like a pretty good percentage. So suppose Messi takes 6 penalty kicks next season. So find the probability that the number he converts is exactly 6, at most 3, and more than 3. So what we're doing, we've got 3 different parts to this question, okay? And this question will prove to be a nice segue into this next subsection. Well, it's actually after this one, but this one right here. We'll start talking about cumulative probability, okay? Okay, so I'm going to go ahead and write out the parameters. So if we're talking about 6 penalty kicks, then the value of n is 6. And the value of p is never going to change. It's 76%. Okay. Guys, I'm not going to write the value of q because I'm not going to be doing these by hand. And then for part A, we're going to find the probability that x is exactly 6. So in other words, that in his next 6 penalty kicks, he makes all of them. Okay. Well, I will probably just use the calculator. Binomial PDF. Okay. And so in this case, n is 6. P is 76%. And then the value for x that we're looking for is 6. Okay. So let's just use our calculator. I think that'll be probably the easiest. In fact, well, what you could do, guys, once you got that in there, you could just hit second and then entry or enter right here, and it'll allow you to replace these values with the ones that you want to use. So I'm just going to do this. You want to make sure, though, you got commas between the values of those parameters, okay? And you want to make sure that this ends with a closed set of parentheses. So now if we hit enter, it gives us that probability. And I'd carry this out to maybe 3 decimal places, so 0.193. Okay, so then you could say that the probability that Messi makes all 6 of his next 6 penalty kicks is about 20%. Okay. All right, now what about for part B? Part B, it says makes at most 3. So what does at most 3 mean? Well, it means he could make 0 of those penalty kicks, he could make only one penalty kick, he could make exactly 2 penalty kicks, or he could make at most exactly 3 penalty kicks. So really what we're looking for here is, what's the probability that x is equal to either 0, well, I'll write it this way, that x is equal to 0, 1, 2, 3, or not 0, 1, 2, or 3, okay? And if you think back to section 3.3, when we were talking about the addition rule, this would become the probability that x is 0 plus the probability that x is 1, because these are mutually exclusive events, right? In the next 6 kicks, he cannot make 0 and also 1, right? He either will not make any of the kicks, or he'll just make 1, or he'll just make 2 of the kicks, or he'll just make 3 of the kicks. Okay, so these are mutually exclusive events. So that's why we can add together these probabilities, plus the probability that he makes exactly 2, plus the probability that he makes exactly 3. Guys, and this, think back to section 4.1. If you were to find the probabilities associated with all the values of our random variable x from 0 all the way to 6, they should all add up to 1. This is you would have a probability distribution then. Okay, so what you could do is you could reuse this just over and over again, okay? All you would really have to change is the value for x right here, correct? Because you've already got the number of trials in there. The probability of success for each of those trials is going to remain the same, and then you can just change the value of x. Just hit enter and enter. Okay, now I want to point out, if I haven't already, that when you get, this is scientific notation, so what this means is you actually move this decimal to the left 4 places. This is like multiplying this number right here by 1 over 10,000. Okay, so if I were to have done that, I would end up getting 0.0002 roughly if I round it to 4 decimal places. Okay, plus, and that's really low probability, because if he's a 78% penalty kicker, it would be extremely rare that he would go 6 kicks and not make a single goal, okay? And then I'll just reuse that same thing. Oh, I don't want to do it that way though. Second, enter again. And let's change that value of x to 1. Enter again. Okay, so now we see the probability increasing a little bit. So this would be 0.0036. Okay, plus the probability that he makes exactly 2. This is where Excel can be very handy, guys, because okay, so this to 4 decimal places would be 0.0287. So there's still not much probability here, right? Because he's such a good kicker that it would be extremely likely that he would only make 2. As these numbers increase, you see more probability. And then finally, we do this last one. Let's replace that value of x with 3, and we get, and this is still, not fairly low, 0.1214. Okay, and then guys, you would just add all these together. Let me also, before I actually add these together, let me also write here that this can also be denoted that you could say, what's the probability that x has a value that's less than or equal to 3? This is actually how it's commonly done, okay? And this is probably the way I'll do it from here on out. But anyway, let's add these values together. Now you can see that because I truncated some digits in each of these, we've lost a little bit of accuracy. So the most accurate that my answer could be is probably only going to be to 3 decimal places, since I rounded these to 4 decimal places. Usually you lose. Well, it depends on some other factors, but you lose a decimal place in accuracy each round of calculations that you do. Okay, so we did something close to this. 0.1539. Okay. All right, so you could say there's about a 15% chance that Messi in the next 6 kicks will miss all of them, or make exactly 1, or make exactly 2, or make exactly 3 of those kicks. All right, and then what about part C? Part C says, what's the probability that he will make more than 3? So here this means, what's the probability that x will take on a value that's strictly greater than 3? And so what this means is the probability that x will take on a value 4, 5, or 6. Okay. So again, we can use that addition rule, because these can be looked at as mutually exclusive events. So the probability that he makes exactly 4 plus the probability, I should be using the correct notation here. I'm writing that x is equal to 4 plus the probability that x is equal to 5 plus the probability that x is equal to 6. Okay. All right, now for this one, you could do these individually the way I did the last one, or you can come over to your, let's see, list. Wait a minute. Yeah, go to second and then the stat key to, or no, I'm sorry guys, just hit the stat key. Okay, now what, I think I've done this previously over here. So what I could do for under list 1 is I could put these different values of x. I could put 4, 5, 6, and then I'll delete that last value. Okay. There we go, 4, 5, and 6. And then I could, well, I deleted my table 2 and I haven't put it back yet, but let me clear this column. Then I could come up here for list 2 or list 3, whichever list you want to use, and you could hit enter, and it'll give you a cursor down here, and you can tell it how you want those values in list 3 that will correspond with those values I've already put in the other list to be calculated. And I want to do it by, I'm going to go get that binomial probability density function. Okay, here it is. And it's 3 trials, P. Right here though, oh wait a minute, no, it's not 3 trials, it's 6, isn't it? Thinking of the last problem. The probability of success is 0.76. And then you want to leave this an x, okay? Wait, is that right? Let me check this first. No, actually, I think that x, you need to put in the list in which you put in those variables for x. So I put those values for x in list 1. So what I need to do is go to second, the stat key, and plug in list 1. Okay, and then I've got my parentheses closed there. Now when I hit enter, it'll generate those corresponding values associated with the probabilities that x is equal to either 4, 5, or 6. So you can do it this way. This would be something similar to doing it in Excel. Okay. let's try one other thing. I think you can do it in your y equals screen. You can let y equals be the probability density function. This actually may be easier for you guys. And you want make sure you leave an x in there, okay? And then just go to your table. No. Oh, wait a minute. Well, I didn't actually put it in here, did I? Let me try this again. Here we go. I never actually, well, now it's changed everything, but yeah, put an X right there. Now I'm going to paste it in there. Okay, so now I've got to put in there. Now if I go to my table, it will, of course, we're not interested in values of X this high, but if I scroll back up, now we're starting to see these probabilities. See, so this is actually the distribution right here, guys. This is a probability distribution. Anyway, you can see these are the same values we got from part B. Okay, so this might be the way to go unless you want to do each of those individually, which isn't bad. But I'm going to copy these in here. I'll round them to 4 decimal places. So when X is 4, associated probability is 0.2883 plus when X is 5, the associated probability is 0.3651 plus, and then finally, when X is 6, 0.1927. So you can see this is where all the probability lies, right, for these larger numbers. And then there's ways you could tell your calculator to sum up these values, but I think we'll just type them in manually. You guys probably didn't know this calculator had so much functionality, did you? And we get 0. Let's go 3 decimal places here. Okay, 0.846. All right. All right. Now, when we get into this next subsection, we're going to look at an easier way of doing these are cumulative probabilities here, because we're trying to, like in this one, we're trying to find the accumulated probability for all the values of X that are less than or equal to 3. Okay, but this is the only way we know how to do it at this point. All right, and we looked at how we could find these using a table. Okay, so last thing, we probably will end this one. We'll do a part 1 and a part 2. Okay. The last thing I want to do right now is constructing a binomial probability distribution. Okay, so we actually already just did that inadvertently. But all you're going to do, guys, is you're just going to find the associated probabilities for each value of X. Okay, so this example 5 here, it says a new medical technique is performed on 7 patients. So N in this case would be 7. P, it says there's a 70% chance of success, so P would be 70%, and then these would be all the values for X. So we just want to find all these associated probabilities with these differing values of X. Okay. Now, this would be a really good time to use your calculator. Okay. So let me go over this again. So go to y equals, this is the easiest way to do it instead of using the lists. Go to y equals, go get your binomial density, binomial probability density function. We've got 7 trials. The probability of success is 70%. And you're going to make sure you have an X right there, because what the calculator is going to do is it's going to be plugging in different values for that X. And under the Y1 column in the table, it will be giving you those probabilities. So this is a function. If you guys remember that whole concept of what it means to be a function from your algebra classes. Anyway, I pasted it in here. I go to the table, and we see these probabilities. Okay. So this first one, it's 2.2 times 10 to the negative fourth. So move that decimal to the left 4 places. So you have 0.00022. And then this next one to 5 decimal places, 0.00357. And you just keep going. 0.025. 0.09724. And then probability that x is 4 is just a lot of writing, for me anyway. And then let's see, 31765. Okay, the probability that x is 6, or in other words, that there's 6 successes out of the 7 patients would be 24706, 0. And then finally, let's scroll down to find that last one, 0.08235. Okay. And guys, if you were to add all of these up, they should give you 1, or at least a number close to 1. Remember, sometimes it may not exactly be 1 because of rounding error. This should be extremely close because this is a discrete probability distribution. Now, once you've got a distribution like this, it's easy to find some of these probabilities. So, part B, find the probability that the surgery is successful for at least 5 patients. Well, this means the probability that x is greater than or equal to 5, because at least 5 patients, and that means 5, 6, or 7, okay, for which that surgery was a success. So what we could do here is we've got all these probabilities already listed for us. So this would be the probability that x is equal to 5 plus the probability that x is equal to 6 plus probability that x is equal to 7. And you can just copy these down or just add them up in your calculator. Okay, so I think I got them all in there. So this gives us about, if we go to 6 decimal places, 0.647. Okay. Look at part C. Find the probability that the surgery is successful for less than 5 patients. Well, guys, this is kind of an interesting one because less than 5 means that x is strictly less than 5. So this means x could be 0, it could be 1. In fact, I'll do it like this, ... plus probability that x is equal to 4. Okay, that would include the probability that x is equal to 1, to 2, to 3, and to 4, but not including 5. Now, you could look at this table, get all 5 of those probabilities individually and add them together, or If you realize that this is a complement to this previous event, then you can say the probability that x is less than 5 would be equal to 1 minus the probability that x is greater than or equal to 5, because we just found that one. Okay, because this, and I'm going to put in here the fact that we're using the fact that these two events are complementary. Okay, to me, it's a lot easier to do it this way. So if you were to do it, it would end up being 1 minus. Now for this part, I'm going to pull more than just 3 decimal places. Let's do 0.647, 06. If we say 1 minus that, now I could round this one to 3. Okay, 0.353. Okay, so guys, try to be on the lookout for stuff like that. And this is very common. Lots of times in working with probability, you'll be asked things like this. And part of it is to exercise your recollection of what it means for two events to be complementary. Okay, because see, both of these events couldn't occur at the same time. There would be no overlap in probability, because this one's strictly less than 5, and this one is greater than or equal to 5. So one of these two events would occur. So anyway, or like I said, if you want to find all these individual ones individually and then add them together, that's fine as well. But anyway, all right, let's see. I think we'll stop this part 1 right here, simply because I'm pretty tired, and this is a good stopping point. So what we'll look at next is cumulative probability. Okay, so you'll realize that in this next section, having known this would have made some of this other stuff go a little quicker. Okay, so I'll see you in part 2.